let's go to the third point, so which is stochastic integral. Let me first introduce why we need to define stochastic integrals. And to introduce the stochastic integrals, let's consider first stochastic differential equation. So as I said in the beginning, we have a differential equation. The derivative with respect to time is equal to some f, and then we have some noise multiplied by g of x, and we will consider white noise. So the average is 0, and the dispersion is given by this. I don't know if you can see well. Okay, and delta t minus t prime. Okay. In mathematicians, as I said before, don't like the white noise. So in many situations, they write, instead of they write the differential equations in this notation. This is a notation where look only at this part. No, we have dx equal f dt. If you divide by dt, here you will get the derivative with respect to time. And if you divide this by dt, you will have the derivative of the Wiener process, which by definition is the white noise. So it's equivalent definition, but why they prefer to write it like that? Because this is also a kind of aberration. We can integrate this, and we can say that these two equations are equivalent to this one. This is not very useful for practical reasons, because this is just the integral of this. No, we integrate this between 0 and t, and then we have the integral between 0 and t of dx dt f x t prime, and then this part. So this is not very practical, because this is to transform a differential equation into an integral equation, which are much harder to calculate. But it is convenient to write the equation like that to see where the problem arises. The problem with the white noise that I mentioned before, that this will require some interpretation, comes because this term is equivalent to perform some integral where we have the integral of a function times the derivative of the Wiener process, and this will have a lot of problems. This if x depends on w, which is the case because the solution of this equation will eventually depend on the noise. So this has some, this x and this w are we will see that sometimes they are independent, but x in principle depends on w. So this integral has a lot of problems, and this is called a stochastic integral. Whenever you have a function integrated with the Wiener process, this is called a stochastic integral. It's a kind of a stochastic version of the Riemann-Stieltjes integral. So why this is a problem? Well, we will see. We have to go really to the foundations of calculus to find out why this is a problem, why this is a problem essentially because dw, as we have seen before, is ill-defined. So we will have some problems defining this. The best, the problem arises because we are trying to integrate something that cannot be integrated. But even though mathematicians insisted and created the stochastic calculus by trying to make sense of this thing. So let's try to make sense of this integral. And to do that, as I said before, we have to go back to really the foundations of calculus. Let me do it in general. We have to integrate between 0 and tau a function of time, but this function is stochastic, and it will depend on Wt eventually, and times the increment of the Wiener process. So if we want to make sense of this expression, we have to go back to the Riemann sums. Remember how we integrate a function? Here I put just a smooth function, but this will be much more complicated. And I want to integrate this function between 0, which is here, and some time tau. what we did in the first courses of calculus is to make a partition. Sorry. We make a partition. So we divide the interval 0 to in small intervals. No, remember the Riemann integral, it was to try to sum rectangles. Here's the area of these rectangles. So the Riemann sum, this partition has a size delta t. So we have the Riemann sums, which is to evaluate the function in some point. And well, this is the Riemann still just sums, because this is dwt, so we have to multiply by the increment. So this dwt is the increment of the Wiener process in a time tk and tk minus 1. Tk is just these points where I've divided the integral, the integral. And tk star is 1 point in the middle of the interval. So tk star is a point which is inside the interval. Do you remember this, the Riemann sums? This is the definition of integral. And the nice thing of the Riemann sums is that when delta t goes to 0, if I do my partition more and more, finer and finer and finer, then the result, the limit of this sum, does not depend on the choice of the point. You remember, you can choose this as the maximum, the minimum, the left, the right, the point in between. Essentially, when you do this, you are here approximating the curve by some steps or by trapezios, I don't know, by rectangles or by triangles and so on. So essentially, if a function is integrable, then it does not depend on the choice. This is the important thing. What happens here is that because this is a strange guy, the limit, it's going to depend on the choice. And then so the integral depends on this choice. And the interpretation that I mentioned at the beginning of the lessons are precisely different choices. So one has the Ito interpretation. Remember, we have two big interpretations. One is the Ito interpretation. And the Ito interpretation means that we perform these sums evaluating the function in the first point. So so tk is the first point of the interval. So I have my interval, and I take always the function at the beginning. This has this is a reasonable choice because we have some causality, no? That that what happens in the future only depends on the. So I have my randomness at the beginning of the interval. So it makes some sense, okay? But it also makes some sense to evaluate the function in the middle point. This is, in Riemann, we know that this is also a nice approximation, no? That we can take the middle point of the two. In this case, since tk is k plus delta t, k times delta t, the middle point will be k minus 1 delta t, okay? And this is called the Stratonovich interpretation. It was introduced by Stratonovich. And these are the two main. There are an infinite number of interpretations. So I could choose any point in between. These two are important for the reasons that we will discuss later on. But there are infinite number. And the point is that this integral, or this one, if we try to define the integral as the limit of this, gives different results. This is it. This is the problem. So this object, if I write this object in mathematics, this has no meaning unless I specify which interpretation. These are called interpretations. Which interpretation, which choice of the point I use. So you have Ito or Stratonovich. There are also Klimontovich, which is the last point, but this is more, these are the two main interpretations that we have. So we have that stochastic integrals can be interpreted in these two ways. And to really show you that the result depends a lot on the choice, I will do an example, a specific example. And the example is going to be the following. Let's try to integrate. You see here I have any function. Let's do, I guess it's the simplest thing that one can imagine. W times dw, okay? This is a typical example to show how different the two interpretations are. Okay, so let's start with Ito. I have my sum, I have my partition. I have a number of the number of intervals is t divided by delta t. And now I evaluate my function in the previous, and I multiply by the increment. Oops. Sorry, here it's wrong. This is w take tk minus w tk minus 1. And well, we could do a lot of things with this. We could take this expression and calculate a lot of things. We are going to calculate the simplest property, which is the average. Okay, so let's calculate the average of this guy. So what is the average? Well, this is very easy, because remember that we have this property that the increment is independent. Sorry, this is w tk w tk minus 1. This is the increment is independent of the initial point. So then this is what we did in the last transparency. This is 0. This factorizes, no, one and the other, and then this is 0. Okay. Look what happens if we do the. Let me erase here. I will keep this just to remember the definition of the integral. Let's try to do the Stratonovich case. So we have to sum again from k equal 1 to t divided by delta tau divided by delta t. And now we have to evaluate the integrand, this w, in the middle point. Okay, let me call the middle point tk star. But now this tk star is, we have to put the Stratonovich one, okay? And now I multiply by the increment. Now I wrote it, okay. And again, let's only calculate the average. So let's calculate the average. This is a simple exercise, because here we have w, and remember what was the result? The minimum of the two. The minimum of the two. Sigma squared, the minimum of the two. Let me rewrite it here. When I have this, the correlation is the minimum of the two times. So now if I go to this guy, what is the minimum? tk star is the middle point. Tk is the last point, and tk minus 1 the first point. So here, the minimum is tk star. So then I have the first is sigma squared tk star. This is this average, okay? And now minus this average. And now I have w tk star, w tk minus 1. Now the minimum of the two, remember the minimum of the two is tk minus 1. So now I have sigma squared tk minus 1. And now, so I have tk star tk minus 1. Oops. Off. I have tk minus 1. And what is this? This is the middle point, and this is the first point. So this is delta t divided by 2. Okay? No, the middle point and the initial point. So I have that this is delta t divided by 2. And now if I sum over all the number of terms is t divided by delta t, this is sigma square, and now tau divided by delta t times delta t divided by 2. So this is tau divided by 2. Okay. So you see, in one case, if I take the Ito, if the integral was a normal integral, the result should be the same. The Riemann sums are independent of the choice. Here, just by this small amount, if I choose the first point, I get 0, and if I choose the middle point, I get sigma squared divided by 2 tau, which can be very big. Can be if tau is big, it can be very big. So this is the first shocking thing of stochastic differential, and this is for integrals, but differential equations will be converted into integrals at some point. So we will have these two interpretations for stochastic differential equations as well. So this is the first shocking part, and to finish this, let's consider, well, this is the result of this integral, no? But this integral, we can do this integral. We could do it using the chain rule of standard calculus. So I have in a standard calculus, what I have how I integrate x dx. So what we do is this is x squared divided by 2, no? This is let's say if I make the derivative of this, I get 2w dw, no? This is the typical chain rule of in a standard calculus. So let's try to do the integral like that. If I do this, I evaluate w in tau, then w in 0, but w, remember, at 0 is 0 by definition. So I get this, and if I average this, what I get sigma squared divided by 2 tau. So the standard calculus gives me the same result as the Stratonovich, but not Ito. So what I get from here is that a standard calculus is compatible with the Stratonovich interpretation, but not with the Ito interpretation. So this means that Ito, although it is a nice interpretation because we are like evaluating the function in the first point and so on, it's incompatible with a standard calculus, with something so basic as the chain rule for derivatives, because this when you calculate this is nothing but the chain rule, no? The derivative of the square of a function is the derivative of the square, which is 2 times x or 2 times w times the derivative of the function. This is no longer true in the Ito interpretation. So this will force us to define a new calculus. And Ito was so brave that he didn't give up and defined a completely new calculus, so a new chain rule, a new way of doing derivatives, let's say, for compatible with these stochastic integrals. And this is the Ito calculus that will be crucial to develop a theory for stochastic differential equations. Okay, so let's finish here. We will next week we will do some. We will continue with the Ito calculus.